In this tutorial, we're going to talk about polynomial functions of higher degrees. So this is our basic definition of polynomial functions. And I'm going to break this down a little bit for you so that you understand what's going on, because it kind of looks like there's a lot. But basically, a polynomial function has a leading exponent, which is called the highest degree. And every term that follows it just decreases by 1. So if the first one, if n is like equal to 2, then this one would be equal to 1. And so on and so forth. So polynomial functions can have a highest exponent of a 20 if you want it to. But it just means that the term that's after that would be 19, and then 18, 17, and etc. until there is no more left. In other words, when you get to the very, very last term, this guy right here, this is called a sub naught. When you have a 0 subscript, it's pronounced not. But there's no more exponent here. In other words, it's 0. So that's kind of what those n's stand for up in the numerator as your exponents. Not numerator, I'm sorry. When you guys look at this n right here, this is just like your term number. So this first entire piece here would be like n equals 1. It's your first term, or if it's larger, then it would be the 10th term. And then this one would just be the one that comes after that. That's all that means. So there's several different polynomial functions that exist. There's tons of them. So this is an example of a polynomial function. So basically, these guys right here, those are those subscripts of n. So this is just my first one, this is my second one, this is my third one, and so on and so forth. Notice too that I am missing the exponents of 7, 6, 5, and 4, but they still exist. It just means that their coefficients, these guys for them, happen to be 0. And of course it goes all the way until you get to a constant value if it is something other than 0. If it is 0, then we just don't see it. So let's go ahead and start talking about the properties. And the first one is that every single polynomial function, no matter what, is continuous. So let's go ahead and figure out what that means first. So in these two pictures, one of them is continuous and one of them is discontinuous. And I'm pretty sure, just based off of your common knowledge, you can figure out which one is which. If you took a look at the graph on the left, I can actually start all the way to the left of the function right here and trace it without lifting up my stylus pen. And that's what continuous means. It basically means that you can trace it from start to finish without ever leaving the piece of paper. If you take a look at the second graph, the one on the right, if I start from the left and work my way over, I get to here and I have to finish that circle, and then I have to lift up my stylus and start over on the right-hand branch. That means it is discontinuous, whereas this guy means it's continuous everywhere. And every single polynomial function is continuous on their entire domains. The second property we're going to talk about is that they have smooth, rounded terms. And here's the basic difference. So if you take a look at the graph on the left, notice that, of course, the parts that they have that are rounded, that are curved, are nice and smooth, right? Whereas in the picture on the right-hand side, this is the absolute value function, but it does go to a very sharp point. That is not a characteristic of polynomial functions. Polynomial functions are always very smooth, they're very fluid. The next property that we're going to talk about is that they can be even or odd. And so what it means for a polynomial function to be even is that its exponent is even. For example, we have x squared, which looks like a parabola. We also have x to the fourth, which is basically a parabola, it's just flatter. That's only for its parent function though. X to the fourth can have a whole lot of rounded terms, 3 to be exact. We could also have x to the sixth, which would just even be flatter in the middle, like that. So these are all even functions, and notice that they all have the same exact axis of symmetry, right down the middle. So all even functions have this characteristic in that they have y-axis symmetry. So when we have these polynomial functions that are odd, that's such functions such as x cubed, which is this guy right here. Or we could have x to the fifth, which is basically the same thing, but it's got a flatter middle. And so we could have x to the seventh, etc., but they all have one common property, in that these all have another kind of symmetry, which is called origin symmetry. In other words, their line of reflection will always be that they reflect across this guy right here. Okay, y equals x. And this takes us into one other important thing about these polynomial functions being odd or even, and that's called the leading coefficient test. And so this is what we're going to talk about here. So if n is odd, that means n cubed, x cubed, or x to the fifth, or x to the seventh. We have a couple different situations that will let us know what to expect from the graph of our polynomial functions. And so basically, if a sub n is greater than 0, so if it's 2, 3, 4, anything like that, we're going to have a graph that falls to the left and rises to the right. Something like this. And the exact opposite happens if a sub n is less than 0. In other words, if it's negative, the graph rises to the left and falls to the right. So the exact opposite would happen here, something like this. So the one in yellow is for positive polynomials. The one in orange represents negative polynomials, only for odd polynomials. If our function is even, such as x squared, x to the fourth, x to the sixth, we have the graph rising to the left and right as long as it's positive. So this is just like our normal x squared parent function, something like that. And if you have a polynomial that's even and the leading coefficient is negative, then you have your function falling to the left and to the right. So basically it's reflected across the x-axis and it's going downward. So smiley face, frowny face. And we have one more property to talk about, and that is their zeros. In other words, their x-intercepts. And what this means is that the graph will have at most n-1 turning points. So let me show you what that means. So if we take a look at our parent function x squared, if I take my exponent, which is 2, and subtract 1 from it, I get 1, which means that there's only one turning point in my function. And sure enough, that's all there is. There's just one turn. Here we have an x to the third power. This is some cubic. It's not our parent function, but it is a cubic function. If we take 3 and subtract 1 from that, I get 2, and sure enough, I have 1, 2 turning points. So jumping ahead, here's x to the fifth. I do 5 minus 1, which gives me 4, and sure enough, I have 1, 2, 3, 4 turning points. So that's also something very interesting about your polynomial functions. And that will conclude this tutorial.